and from Italy. The presentation title is Abnormal Absorption of the Hydrogen in Nickel and Ambient Temperature with Associated Emission of the Neutrons. Please.
Okay, can you hear me?
Yeah, it's clear.
Okay. Then the presentation subject is abnormal absorption of hydrogen in nickel at ambient temperature with associated emission of neutrons. The content of the presentation consists of the following points: system setup, sample description, absorption test, data evaluation, nuclear signature, neutron detection, and final remarks. Reactor 1 setup. Reactor 1 consists of a steel chamber with a volume of 290 cubic centimeters, inside which is a glass tube wrapped with a resistor that serves as heater. The material to be tested can be housed in the tube. A PT100 in contact with the material allows the control of its temperature. We also have a thin film resistance here, a thin film resistance that allows to check if we have hydrogen or deuterium inside the reactor. In the photos on the right of the setup, we have respectively the sample holder here, the sample holder and the thin film resistance here, and the nickel strip, the nickel strip folded several times, and then the material inside the glass tube here. Pressure monitoring. Here we have represented the scheme for detecting the pressure inside the reactor. Pressure is the most important parameter for controlling the absorption of hydrogen by the sample. For this purpose, we have a piezoelectric sensor here that measures the pressure and an interface that displays its value and is connected to the computer that controls the experimental parameters. Reactor 1 control interface. In this screenshot of an example of how the computer can control what happens into the reactor, we have the most important parameters that allow to follow the progress of the experiment. In particular, we have three windows. In the top left, we have two parameters: the power sent to the heater and the temperature of the sample. In the top right window, we have the ambient temperature and the reactor temperature. Then in the bottom right window, we have two important parameters, which are the value of the thin film palladium resistance, which allows to know if we have the correct gas inside the reactor, and then the pressure trend inside the reactor. Pressure is the most important parameter for checking absorption. Sorry, the slide was this. And next, neutron detection, sample description. The used sample was a nickel strip with a deposit of 200 nanometers of palladium on both sides by electroplating. The weight of the nickel sample was 0.63 grams. The sample was folded several times to be able to introduce it into the glass tube, on which a heating resistor is wound. The heating was used in the degassing phase of the material under vacuum before introducing hydrogen. Then the absorption experiment continued at room temperature, which remained fairly stable fairly stable around 22 degrees centigrade. Absorption test. The graph on the left shows a clear absorption of hydrogen introduced into the reactor at a pressure of 315 millibar. In about 2 hours and 30 minutes, you can see on the x-axis, the pressure dropped down to 147 millibar. The black curve illustrates this trend. Taking into account that the absorption of hydrogen by the small amount of palladium deposited on the nickel would have been able to make the pressure drop by about only 3 millibar, it is evident that the reduction in pressure is mainly due to hydrogen absorption by the nickel. The red curve indicates the increase of the value of the thin film palladium resistance always into the reactor to monitor the presence of hydrogen or deuterium. Absorption test in previous experiments with a different nickel sample. The graph in this slide, we have another example of nickel absorption in a previous experiment where the sample was a 0.5 gram nickel sponge with palladium deposition. We see that, as in the case of the experiment with the nickel strip, the first absorption is consistent, even if it begins about 2 hours after the hydrogen has been introduced. The hydrogen input, in fact, is in correspondence with the rise of the thin film palladium resistance, is the red curve, as indicated by the red trace in the graph. Absorption data evaluation. The volume in liters of the absorbed gas is obtained multiplying the ratio between the delta pressure and standard pressure at ambient temperature by the volume of the reactor. Then the ratio between this volume and the standard volume of 1 mole of gas gives the hydrogen absorbed moles, dividing the H moles by the nickel moles gives the hydrogen over nickel ratio. After the first absorption, hydrogen refill brought the pressure to 0.98 bar, and after the second absorption to 0.981 bar. Here below the calculation of the total absorption, you can see here that we had 3 different phases of absorption, and this is the total calculation. So the absorbed ratio, the ratio between hydrogen and nickel was 0.60, 0.6. Neutron detection setup. In this slide, we have a photo of the reactor with a Ludlum helium-3 neutron detector underneath. You can see here. It is interfaced to a PC on which the number of neutrons per minute and the number of neutrons per hour are tracked. This allows us to check if there are any anomalous neutron emission, as we will see in the next slide. In this slide, we see the graph of the trend of neutrons per minute and the neutrons per hour recorded by the neutron detector seen in the previous slide. In particular, the neutrons every hour are plotted with the green dots united by the green line, and it is clearly seen that at a certain point, when hydrogen was introduced into the reactor, the number of neutrons every hour is significantly increased, as we will be better shown in the histogram in the next slide. Here below, there is just the description how the neutrons are plotted. Nuclear signature. During the absorption test, the neutron hour counts showed an increase of about 80%. This situation has also been verified several times with samples having similar structure. So in the neutron hour histogram below on the left, there are two distinct data populations. While for a reactor without hydrogen, the neutron hour histogram below on the right basically overlaps the background. You can consider that the neutron monitoring is always active in my lab. Final remarks. In previous experiments, the ability of nickel sample of which a thin layer of palladium was electrodeposited to absorb hydrogen, even at room temperature, in a considerable quantities, was verified several times. I presented work on this in other conferences, using nickel foam and nickel thin wire samples. Once more, the unexpected ability to absorb hydrogen at room temperature of such kind of structure was verified in a different nickel sample, in particular a strip of 12 square centimeter of surface and 0.15 millimeters thickness. In the specific, the pressure decrease at the end of the 3 successive phases of absorption has been about 254 millibar. The volume was 72 cubic centimeter in a volume of hydrogen for a reactor volume of 290 cubic centimeters, such as to bring the ratio between hydrogen and nickel atom to a value around 0.6, despite the fact that the deposition of palladium was not particularly uniform. So the absorption was not due to the entire surface. Neutron emission was associated to a hydrogen absorption and was clearly detectable not only during the absorption phase, which lasted several hours, but also until the sample remained in hydrogen atmosphere. Thank you very much for your attention.
Okay, thank you. You have still a few minutes. We open for discussion. Anyone has questions? Yeah, please raise your hand. Okay, I will give you a chance. Okay. Anyone?
Can you hear me, Professor Mastro?
Yeah.
Yes, I can hear you very well.
Thank you for your presentation. And for the histogram, as I understood, you believe that there are different kind of neutrons, even if the global counting is similar to the background. The quality of the neutrons are distinct. Is that correct, as I understood from your presentation?
Can you repeat your question, because I lose the sound for a moment.
Okay. You are saying that even if the count is not very different from the background, the histogram is too different from background. So you believe that the sample is producing some neutrons. Is that correct?
That is correct. In this experiment, we had only a quite low increase of the neutron emission, but I had different experiments where the neutron production was much more. But when I have inside this reactor a sample with a similar structure, I see always some excess of neutron respect to the background. When there is no sample inside the reactor, we have the histogram of the distribution of neutrons overlapping plus or minus the background that you can see here in dotted line. Okay, is it enough?
Yes, and what about the other emissions, X-ray and gamma rays? What are your conclusions?
Gamma rays?
Yes.
Yes, I have we can see that here, I have always a multi-channel gamma detector that together with the neutron detector monitors about gamma emissions. I never saw any gamma emission moving from the background. This is a multi-channel gamma detector that is inside a LED screen to avoid to increase to match the background due to the cosmic radiation. So here we have the aperture just directed to the reactor to monitor the eventually gamma emissions.
Okay, so do you have any theory about what is causing this weak neutron emission?
I really don't know.
Okay,
Thank you.
you.
As an experimentalist, I just measure what happens, but I don't know what is the reason.
Ubaldo, this is Jean-Paul Liberian speaking.
Hi, Jean-Paul.
How can you make sure that the reaction is not happening in the palladium film? You have a palladium thin film at the surface of the nickel, so maybe the reaction is there and not in the nickel.
Good, very good question. I suspect that neutron emission is due only to palladium.
Okay.
Because I can see burst of neutron emission when the temperature changes a little bit. And changing the temperature, the sample can outgas hydrogen from palladium, not from nickel. Nickel is not easy to evacuate from the hydrogen absorbed, you know. So these experiments are important because when you have the nickel absorption inside the nickel, you can extract the sample from the reactor and make other experiments on the sample because the hydrogen stay still inside the nickel. So the only moving hydrogen when the temperature changes is from the thin film of palladium that is deposited on the nickel.
Okay, thank you. Last question, how do you deposit the palladium? By electrodeposition or by vapor deposition?
By electroplating.
Electroplating, okay, thank you.
So, okay, time is over. Then we switch to the next talker. The next one will be given by